Okay, so again, sorry for the late start, but today we're going to be jumping back into where we left off last time, which is operational amplifiers. So we're done with nodal and mesh analysis, at least learning new techniques. We're not going to be done with it in general. We're still going to need to use it for different types of problems. You're going to be using stuff from chapters 2 and chapter 3 all throughout the class because, for example, when we talk about, operational amplifiers, there's going to be a lot of cases where the operational amplifier allows us to set up the model of the circuit, and then we have to solve that. So you'll go back to the old methods that you used. So an op-amp is the first active device that we're learning about. Does anybody know what the difference between an active and a passive device is? Essentially, active means that it's a powered device. Okay? An amplifier has an external power source that's applied to it, and that's the reason why we can generate a higher voltage or a higher current output than whatever is given to it by the input source. So the operational amplifier looks like this, or at least this is the symbol that we use to represent it. So there's 5 terminals that normally we have to be familiar with. VCC plus and VCC minus, those are the supplies. Those, for example, those of you who are in ENG212, you're using the LM or the UA741 op-amp, and what are the supplies for that? Have you guys gotten to that part yet? You still haven't? Okay. You have? No. But you know? So a transformer works very differently. A transformer is, first off, allows you to step up and step down AC voltages only. It doesn't work for non-sinusoidal, well, it doesn't work for anything that's not alternating current. And it's a set of coupled coils, and so the ratio between the turns in those coils allows you to step up voltage, but there's a corresponding step down in current, which does not apply for the amplifier. So if the voltage goes from 1 to 10, then the current will go from 10 to 1. The input power and the output power should be equal, assuming that the efficiency is 100%. In reality, the output will be slightly lower. Amplifier, that doesn't apply, right? You could have a signal with a power of 10 milliwatts coming in, and you could have a signal going out with 100 watts power going out. And then obviously the amplifier works for DC, AC, essentially anything that stays in between, stays within the linear range. Going back to the previous question that I asked, normally it's positive or negative 12 volts, positive or negative 15 volts. Sometimes for digital circuits you'll see plus or minus 5 volts or 0 and 5. Those are common values for the supplies. How do we model an op-amp? We talked about this circuit right here. This is a very, very basic way to model an op-amp, or the internal mechanism of an op-amp, using a dependent voltage source. We're going to mostly in this class focus on voltage amplifiers. There are other kinds. There's something called a transconductance amplifier, which measures voltage and generates a current, but we're going to be focusing mostly on voltage amplifiers. And then we got to this question here. So we didn't get very far into talking about amplifiers. We stopped talking about what does this value of AO correspond to. Right, you see this value here. AO, or A naught, is the gain that we have associated with the dependent voltage source. And so what does that physically represent? If we go down here and we take a look at the way this circuit reacts, and we did this last time, the way that this circuit reacts if we have no load applied, meaning if I get rid of that, pull that out, we end up with a ratio of V out over V in equals A naught, or A0. So that gain that's associated with the dependent voltage source, we can also call that the open circuit gain, or the no load gain. All right. So now, so where does that leave us? Let's ask ourselves another question now. What about the case when there is a load being applied? So what is the ratio of V out over Vs when a load is present? And so in order to do that, I'm not going to redraw the circuit again. Let's go back and take a look at the one from last time. So we're still using this circuit right here. Okay, so there's two separate circuits that we need to look at. Let's take a step back for 1 second. This thing froze. Okay, thank you. Okay. So let's take a step back here. And I want to write down what are the assumptions we have for this equation, because there's more than one assumption. We have the assumption one is that our R out is equal to infinity. And the second, and it's not really an assumption, but that we're concerned with V in and not Vs. So what does that mean? If you take a look at the circuit up here, this is V in and this is Vs. They're two different values. So Vs is the source voltage that's being applied, and V in is the input voltage that's being read by the amplifier. There's a source resistance between the two of them, and this agrees with the way that we generally represent sources as what is called a Thevenin type source. We haven't gone over that yet, but we'll be going over that very soon. So the question here asks, what is the ratio between V out and V in? Not what is the ratio between V out and the source voltage that's being applied. And it's when you are working with the circuit, you're going to be applying the source voltage. Okay, you're not going to be applying the input voltage. The source voltage is what you're going to be applying. So the next question, the way that it's a little bit different, is it changes in one way. The second assumption was that we're concerned in this equation here with V in and not with Vs. So now let's get rid of the second assumption and keep the first one. So now let's figure out what is the ratio between V out and Vs. So what is the ratio V out, Vs when R in is not equal to 0? We will keep R out equal to infinity for now. All right? So now let's go back to this. We are going to use KVL again, and we're going to need to come up with two different expressions, one to describe the left-hand side, one to describe the right-hand side. So I'm going to write that down. I'm going to say left, and I'm going to say right. And I'm going to draw a line down the middle. On the left-hand side, we're going to be concerned with what's the relationship, or what is the definition of V in. And on the right-hand side, we're going to be concerned with what is the definition of V out. So let's go back here for a second. How do we define V in terms of Vs? What does that look like? It's the kind of circuit we've seen before. Right, the left-hand side has a name. Hopefully by now you guys all know that name. It is a voltage divider, yes. So V in is equal to Vs times Rin over Rs plus Rin. So it's equal to Vs over Rin, can't write today, over Rs plus Rin. Our right-hand side, we're still keeping the assumption, you know what, there's no point. Might as well do the whole thing now as opposed to breaking it down to a million steps. So what's the value of ratio of V out over Vs when R in is not equal to 0, and we'll get rid of the other assumption, R out is not equal to infinity. Let's do the whole thing now. So assuming that R out is not equal to infinity, if we go back to this here, what is the ratio between V out and V in? It's another voltage divider, right? So what we have is AO V in, because that's our dependent source that's provided to the voltage divider. And that'll be R, what did I call it? R out or RL? R out over, let me look to make sure the names. Okay, I call it RL. So this is RL over RO plus RL. And then, if I take the two and combine them together, that'll give me my full expression. So I take V in right here, and I will plug that in right there. And so the full expression for both sides will look like V out equals AO. Now let's plug in for V in. Vs R in over Rs plus R in. Now can't forget the other voltage divider, RL. So this expression here describes the effect of the input and the output resistances. All right. Now, that's not a very nice looking expression. And what do I mean by that? Right? So the gain for this, all I have to do in order to get the gain is just get rid of that and move it over there. So the gain is AO Rn over Rs plus Rn times RL divided by RO plus RL. There's a lot of problems with this expression if you're talking about building an amplifier to use physically. Right? Do you want the gain of your amplifier changing with your load? It's not a very desirable trait, okay? Especially when you talk about working with a speaker or something like that. So we want to figure out, is there some way we can make this look a little bit more like a constant number? The idea is that you want an amplifier that just multiplies by 10, multiplies by 20, right? You want it to be just static. So how can we improve the performance and make the gain independent of the source and the load? And for this, we're going to use a technique which is called impedance matching. In other words, we will choose values of the impedances, and depends on which ones we have control over. We will choose impedance values to fit our desired operation. I could go into a little bit more detail and give a more formal definition of impedance matching, but for the time being, this is good enough for our purposes. So now, let's take an example, okay? And I'm going to try to split this example into almost like a weird timeline type thing. So, first thing is you are given let's say a source with RS equals 10, well, kiloohms, and you want to use a load that is somewhere in the range of should I say 10 kiloohms again? $10 kiloohms. Okay. So you know what your source and you know what your load are. Step number 2. You can choose an amplifier to fit those characteristics. And I'm going to replace these equals with approximately equal to, meaning it's going to be somewhere in that range. So now, how do we choose an amp to fit those characteristics? So I'm going to write this expression, the one we used before. So we have V out over Vs equals So that's the expression we had so far. Now, the way that we can get rid of the effect of the load on the source is to simplify those two fractions, the second and the third one, down to a 1. So how could we do that? If Rn is significantly greater than Rs, then this will all simplify down to a 1, right? If you have 1,000 over 1 plus 1,000, that's approximately equal to 1. Over here, if we have a relationship where RL is significantly greater than RO, then again it simplifies down to 1, and what we will get is this is equal to AO. And so these are the two rules that we can use when we're choosing. These are going to be the guidelines for our impedance matching. So we're going to choose an amp to fit those characteristics. So we want to have an R input that's significantly greater than 10 kiloohms. And we want to have an R output that is significantly less than 10 kiloohms. Remember that the source resistance and the load resistance are external to the amplifier. The input and the output resistance are internal to the amplifier. And so you'll be able to find these values on the data sheet for an amplifier that you're looking at. All right? And there'll be different values depending on what type of amplifier it is and what its intended purpose is. So we choose an amp to fit those characteristics. And then we end up with a much nicer expression, right? We end up with VO over VS is equal to whatever this intended gain is. So does that process make sense? Right? And that's how we take that complicated expression and simplify it. All right. So now we're going to switch gears for a second. And we're going to talk about some fundamental op-amp based circuits. This representation right here, this model, or it's on the other, in the previous set of notes, is going to work for some types of problems, but it doesn't really allow us to control the gain. It doesn't allow us to determine how the op-amp is configured inside of a real circuit. And so what we want to do is take a look at some of the practical configurations that are used in hardware. Who's ever heard the name inverting or non-inverting amplifier configuration before? Sounds familiar? Somewhat? Okay. So what we're going to do is we're going to go through a set of what are called closed loop configurations for op-amps that give us certain characteristics. So the first one is the inverting op-amp. And we are going to we are going to examine the way that these circuits work as an example. So the first example is the non-inverting op-amp. And our goal is to define V out over Vs for this non-inverting op-amp. So the circuit looks like this. Okay, this is our source. We're going to call this Vs. We have our Rs, which we are going to assume equals 0. I got to move this down. I'm not going to have space. Okay. And so this feeds into our actual amplifier. So we'll draw this here. Sorry, I'm just seeing if one piece is missing from this, but I think we're okay. All right. And so this is called our R. We're going to call that our R1 value. We're going to call that our feedback resistance. This is our output right here. And I'll give the rest of these points names just to make things easier. So I'm going to call this point A. I'm going to call this point B. I'm going to call this over here point C. And I'm going to call this right here point D. So I wrote the wrong name up top. This is the inverting configuration, not the non-inverting. And so our output is referred to ground. So the output is a single-ended value referred to whatever the ground is for the VCC source, which we can draw, but it's not going to come into play for our analysis. All right, so how are we going to solve for the gain of this amplifier, of this configuration? So the first thing that we're going to do we're going to substitute in our equivalent circuit for the op-amp. The equivalent circuit that I'm talking about is this one right here. Okay, we said that this op-amp, given some assumptions, right, gives us a relatively good representation of the way that an op-amp works. So this piece here, if we cut like that, all right, we're going to take that chunk and insert it in the other circuit. And so where will we be cutting? Again, we're going to be cutting right where the amp is. So that means it's almost like we'll be taking scissors and cutting that chunk out right there. At points A, B, and D is where we are going to cut. All right, so let's redraw this. So this is our RS, which I can actually stop in drawing because RS we said equals 0, so it's not going to have an effect on what's going on. Our VS is still there. We have our, and I'll give this a name as well. I'll call this right here point E, or yeah, E. Zoom out just a little bit so I can see both. Okay, so this is R1. I'm going to go ahead and draw our RF. And I'll label our points. So this is point B, this is point D, this is point E, this is point C. And so our V out is right here. But I haven't included the amplifier yet. The amplifier is connected right here, right? It branches off right there. So now that's where I'm going to insert the equivalent circuit. So how does the equivalent circuit look? It's essentially an input resistance. So this is R in, and it has a voltage V in across it. There is a dependent voltage source. Whose generated voltage is A out, or A naught times V in. Let me erase this for a second just so I have some space. We'll have our R out value. And that's the output of the op-amp. So let me connect those 2 points. All right, so all this in here this is the op-amp. And that's the same thing. That's captured in there. We're given the assumption that this is equal to 0, so this goes away. All right, so now there's one last piece we have to include, and that's our load. Our load is going to be connected at the output. So I know this circuit seems like a little bit out of left field. I think that this is one that you have to take a look at on your own and sort of compare 3 different circuits. You're going to compare the circuit that's right here, okay, this, compare it to this, all right, and then the combination of the 2 gives you this right here. So what we've done is we've taken, yes, say it again. V out is at point D. I had it written, but I erased it. Right, because V out in the picture above is between point D and ground, and so point D and ground. And just to make it match a little bit more, let me add a load to this configuration over here. So I'll give him a load. All right. So now that we have our equivalent circuit, the next thing that we have to do is we have to analyze it. Now, there's one thing before we continue on with the circuit that I want to talk about. And those are the ideal characteristics of an op-amp. Okay? And so, for most problems, you can assume that these characteristics apply, unless they tell you that it doesn't. So what are the characteristics? The first characteristic is no, that was right. Infinite input impedance. And if you look back at what we did up here, you see that if we have an infinite input impedance, that would automatically always get rid of that ratio, because Rin being infinite, it would always be much, much larger than the source resistance. Second ideal characteristic is 0. And I'm going to say one little adjacent thing here. If the input impedance is infinite, that means that the input current will be 0. That's not a different characteristic. That's just a side effect of that characteristic, right? Any path that has an infinite impedance won't have any current flowing through it. It's an open circuit. Second characteristic is 0 output impedance. So we'll say RO equals 0. If we go back over here to this equation, you'll see that now that second assumption gets rid of the other ratio, right? If RO is equal to 0, then it's always going to be significantly less than whatever the load is. What's the side effect of that? The side effect is that the output voltage will equal, so V out will equal A naught times V in, right? Okay, the third one is going to be infinite open loop gain. So this value here is going to be equal to infinity, which may not seem like intuitively a good thing right off the bat, But we'll see how that comes into play later on when we talk about the closed loop configurations. And then the others are a little bit easier to understand. So infinite bandwidth, all that means is that, does anybody know what bandwidth means, what that term refers to? So bandwidth is the range over which the device operates in a certain way. And so infinite bandwidth just means that it works the same regardless of what the frequency of the input is, going all the way from DC to infinitely high frequencies. That's not the way real amplifiers work. Real amplifiers do have a frequency response, and so you have to be cognizant of that when you create a design. Zero offset voltage, what that means is that if we look at this amp up here, and I were to take the two terminals here and tie them together, the output should be equal to 0, right? V out is equal to, regardless of what this value is, even if it's infinite, V2 minus V1, if they're the same, it's equal to 0. The problem is that for most real amplifiers, there is an additional term in there, a small little offset voltage that is associated or is a side effect of imperfections in designing the differential input stage of the amplifier. Okay? It's like if I tell you, I want you to make me a shelf that's perfectly level. Okay? It's never going to be perfectly level. The gains of the two sides of the input stage are never going to be exactly the same. So even when these two values are the same, there's still going to be a little bit of a mismatch in there. But for the purposes of an ideal amplifier, we're going to assume that that offset voltage doesn't exist. So the offset is essentially whatever the input voltage is when the positive and negative terminals are tied together. Does that make sense? Okay. Everyone looks very bored right now. Wake up, get some coffee if you need to step out for a second. I understand it's a rainy morning. This is not the most exciting subject, but hey, I got to teach it, right? You should feel bad for me. Okay. So the characteristics of the ideal op-amp. Infinite input impedance, zero output impedance, infinite open loop gain, infinite bandwidth, zero offset voltage, and there's some other smaller ones that are usually thrown in there, but I think this is the main 5. Okay, so now let's go back to the problem that we're working on. And let's ask ourselves the question, well, why do we need a closed loop configuration anyway? Why don't we just use the op-amp the way that it is? Can anybody tell me? Is an amplifier with an infinite gain going to be very useful to us? Not really, right? We're normally not trying to multiply things by infinity, and no amp can do that anyway. So when you say multiply something by infinity, all that really means is just make the amp saturate. Whatever the maximum voltage is it can put out, always put out the maximum voltage. That's not useful, okay? Because if we have a signal coming in, you just get a straight line. So closed loop configurations, which is what we're already talking about. we use what's called negative feedback to reduce the closed loop gain down from infinity to a finite value that we can use practically. So we have an op-amp, looks like this. The gain for this op-amp equals infinity. What we do is place some other stuff around it. So that the bigger circle, for that, the gain, which I'll call A star or something like that, will be equal to a finite constant value. All right, so that's what we're trying to do with all of these closed loop configurations that we're going to be talking about. So open loop is what's inside the green. And closed loop is what's inside the orange. So when we talk about open loop configuration, that's the amp by itself. When we talk about a closed loop configuration, that is the amp with external components. Since we said negative feedback, that implies, right, that we're tying V out back to V minus. And so you can see here, this is the negative feedback path. And so the way that it works, which we're going to go into more detail when we get back to the example that we were going over, is that as the output gets larger, the negative input gets larger, which is then reducing the V2 minus V1 or the V plus minus V minus. Okay, so the example that we're looking at now, that we paused for a second.
Go back down a little bit.
Yeah. So the example that we're looking at right now that we paused for a second is looking at a closed loop configuration, specifically the inverting op-amp, which we need because the ideal characteristic of an op-amp in its open loop configuration has a gain of infinity. There's a lot of new terminology in there, so I recommend that you spend some time maybe reading over the first few pages of this chapter. It goes into more detail, closed loop, open loop. Again, just getting you more familiar with those terms. All right, so now going back to the example that we're doing. So this is a closed loop configuration. RF is our feedback, our negative feedback resistance. And our open loop configuration is what's included inside of the orange dotted line. We took that and we replaced that with our equivalent circuit. And now what we're trying to do is we're trying to solve for what the closed loop gain is going to be. All right. So next step. Let's apply the ideal op-amp characteristics here. One relevant one is that R in, we've already said, should be equal to infinity, so I in will be equal to 0. I in up here would look like that. Second is that our R out is equal to 0. So V out will be equal to A naught times V in, which we've already drawn that on the picture here. And then third, we're going to say, and this one is an important one, we know that the open loop gain will be equal to infinity. So this one's a little bit harder to figure out. So all right, let's spend a second talking about that. First things first is that, right, in this picture up here, point A is the same as V plus, what we call in the other picture, and point B is the same as V minus, right? If you go back to this picture here, we call them V plus and V minus. All right. So, but the question remains, but why? That's not an obvious jump. The open loop gain is equal to infinity. V plus minus V minus equals 0. Okay, no. Can't just accept that. So the logic works like this. We want a finite output, so V out less than infinity. Right? That I think everyone can agree with. And in fact, so what value, okay, so we want a finite output. We also know that V plus minus V minus is equal to V out divided by A naught. Right? That's one of the fundamental expressions for the op-amp. Where this is infinity. Therefore, the only case where V out is finite is if V plus minus V minus equals 0. There's only one value you can multiply by infinity and get a finite value. 0. Right? 0.000001 times infinity equals infinity. So this third expression here is a side effect of two sort of mini assumptions. The one being, and they're all written in the purple, we want a finite output, and we know that the gain is infinite. Oh, man. All right. So those are the three assumptions or three ideal characteristics that we can use. Now, how is that going to change our circuit? So what I'm going to do is I'm going to copy it. Every time I figure out how to copy it, I forget. There we go, copy. All right. All right, paste. Sorry, it's going to take me a second to get this in the right spot. All right, that should be good enough. Okay, so now, and I'm going to erase this right here. We don't need this anymore. Okay, so let's apply them one by one. We know that I in is equal to 0. So essentially what that means is that this path is going to go away. Right? We know that there's no current flowing along that path. I in equals 0. Second, we know that R out equals 0. We've already included that in there. And then the last is going to be VB equals 0. Now, why is that? Can anybody take a look at that picture and tell me why VB equals 0? Remember, we had three assumptions. The input resistance is infinite, so there's no input current. The output resistance is 0. And then that because the open loop gain is infinite, V plus and V minus are at the same potential, same voltage potential. VA is point V plus, VB is point V minus. Why is VB equal to 0? Yes?
Is it because VA or the V plus is also equal to 0 because it's just grounded?
Right, this is grounded. We know those 2 points are at the same potential, so we know VB is equal to 0. And so this is what our revised circuit looks like. Okay? And you know what? In the example that I'm doing, we don't have a load, so I want to stick to the way that we were doing it. The load's not going to make the problem that much more difficult, but I don't want to throw in unnecessary complications. So we'll do it without the load for now. Okay, so we have a circuit. Are we almost done? We're close, right? It's 10:42. All right, so the last thing we'll do is we will draw this circuit in a little bit of a nicer looking fashion. So let's take this circuit right here. I'll draw it a little bit smaller. And so that is what's left over from what's drawn to the left. So we took the circuit that was here. We replaced the op-amp with the equivalent circuit. We applied the ideal characteristics of an op-amp to simplify that circuit, which is what's shown in the red. And then when we redraw what's left over, it just looks like that. So what we're going to pick up next time is we're going to solve this circuit, and that'll give us the closed loop gain. Yes? So VB is 0, going all the way back up here. So VB, I'm just going to do it on this side since the video is watching this side. So VB is the same as V minus. VA is the same as V plus. The third assumption, without going through the whole spiel again, tells us that the potential at VA, that VA or V plus minus V minus equals 0, or V plus and V minus are at the same potential. So since we can see that point A is grounded, we also know that the voltage at point B is grounded. They're both 0, yes. Just A isn't shown in our figure. And the name that we're going to use to refer to that is we're going to call it a virtual short. Because one way you can think about this is there being a short circuit between those 2 points. But it's a virtual short because no current can flow between them. None of that current can flow to ground. So next time we will pick up there, and I'll have your exams for you. And yeah, sure. Like all the way down to the bottom? There we go. So this is the one that we're going to pick up with next time.